Hey guys, I am Santosh Babanrao Gaikwad, working as an assistant professor, Department of Chemistry, at Punlikrao Gauri Arts and Science College, Shirpur Jain, District, Washim. In previous lecture, we discussed about introductory part of thermodynamics and we studied two most important expression for work done in isothermal and adiabatic process of gas. For these lectures, links are given in description box. In today's lecture, we take a overlook on heat capacity at constant volume and constant pressure, as well as we study one of the most important expression for the relationship between pressure and volume. In next lecture, we study two most important expression for the relationship between pressure and temperature and volume with temperature. Now we study about expression showing relationship between pressure, volume and temperature. We can't study their relationship simultaneously. Hence, we study in different expressions, that is relationship between pressure and volume, volume with temperature and pressure with temperature. Before this, we go towards these three expressions, we have to know some basic terms used in these expressions like what is Cp, what is Cv, what is relationship between Cp and Cv. After these terms, we study expressions of relationship between pressure and volume. We start with the heat capacity of the gas molecule. But what is the heat capacity? It is defined as the amount of heat energy required to raise the temperature of material or body or substance by 1 degree. Heat capacity depends upon amount of material in system. If the amount of substance is 1 gram, the heat capacity is the same as the specific heat. It is represented as symbol C. An amount of heat energy required to increase temperature of 1 gram mole material by 1 degree, this is known as molar heat capacity. When the gas is heated, ordinarily there is an increase in volume as well as pressure in addition to the rise of temperature. For the sake of simplicity, either the volume or the pressure may be kept constant. Therefore, a gas has two heat capacities, that is heat capacity at constant volume and another is heat capacity at constant pressure. Now we know about what is heat capacity at constant pressure. Amount of heat energy required to raise temperature of 1 gram mole substance of or body or material by 1 degree at constant pressure. This is known as molar heat capacity at constant pressure. This is denoted by Cp. Now we study about another term is what is the heat capacity at constant volume. Amount of heat energy required to increase temperature of the 1 gram mole substance or body or material by 1 degree at constant volume. This is known as heat capacity at constant volume. It is denoted by Cv. Now we study what is the relationship between Cp and Cv, or why Cp is greater than Cv. Consider a 1 gram of mole of gas having a volume V in ml at pressure P in dyne per centimeter square and temperature T in Kelvin, contained in the cylinder enclosed by the piston, as shown in animation which we can see above my head. P2 is the external pressure applied on the piston. P1 is a pressure applied on the piston by the gas or system. And V1 and V2 are the initial and final volume of the gas molecules. The heat energy supplied to the monoatomic molecule, that is single atom containing molecule, is used in increase the speed and kinetic energy of the molecules. There cannot be any absorption in the vibrational and rotational energy, and further no energy can be utilized to do any mechanical work as the volume remains constant. That is, if we kept volume constant, then it increases the temperature of the system or gas only. In second case, if instead of volume the pressure is kept constant and the volume is allowed to increase or vary, then the heat supplied now do two things. First is it rises the temperature of the gas, and the second is it does work in expanding the gas against external pressure. The amount of heat required to raise the temperature of the gas in the case is same as in the first case, that is when the volume is kept constant. But in addition, more heat energy has to supply to the external work. Hence, heat capacity at constant pressure is greater than the heat capacity at constant volume by an amount which is thermally equivalent of the work done in expanding the gas against thermal work. We are not going to the deep in expression for the study relationship between Cp and Cv. For this comparative discussion, we can write here Cp is equals to Cv plus Nr. After rearranging this equation, we can write here Cp minus Cv is equals to Nr, where Cp and Cv are the heat capacity at constant pressure and volume respectively, as we know. N is the number of moles of the gas molecules and R is the Rydberg constant. Another equation for the ratio of heat capacity is given here, which we are using in our next three expressions. That is Cp divided by Cv is equals to gamma. Gamma, or this ratio, is also known as azeotropic expansion factor. We come to our most important first expression showing relationship between pressure and volume. From previous lecture, we know that U is equals to dW, which is equals to P dV, which is equals to C dt, and which is equals to minus nRT dln V. From this equation, we choose two equations for the study of the relationship between pressure and volume. That is Cv dt is equals to minus nRT dln V, which is equation number first. For n mole of ideal gas equation is Pv is equals to nRT. Integrate ideal gas equation, that is Pv is equals to nRT, then we get Pdv plus Vdp is equals to nR dt. After rearranging this equation and nR moves to left hand side and it comes to denominator to the Pdv plus Vdp, then we get dt is equals to P divided by nR into dV plus V divided by nR into dP. For getting the value of P and V, we rearrange the ideal gas equation and put these values, that is nRT upon V instead of P and nRT upon P instead of V, then we get dt is equals to nRT upon V into 1 by nR into dV plus nRT upon P into 1 upon nR into PV. After rearranging this equation, for our simplicity, we get here dt is equals to T into nR upon nR into dV upon V plus T into nR upon nR into dP upon P. nR upon nR get cancelled. Also, we replaced dV upon V and dP upon P with dln V and dln P respectively. Then we get dt is equals to T into dln V plus T into dln P, equation number 2. Putting this equation number 2 in equation number 1, that is value of dt in equation number 1, which is equation number 1 is Cv dt is equals to minus nRT dln V. Then we get Cv into T dln V plus T dln P, which is equals to minus nRT dln V. Multiply by Cv to inside the bracket value, then we get Cv into T dln V plus T dln P is equals to minus nRT dln V. After rearranging this equation, we get Cvt dln P is equals to minus nRT dln V minus Cvt dln V. We can see here. Rearrange the left hand side and bring negative charge outside the bracket. We get Cvt dln P, which is equals to minus nRT dln V plus Cvt dln V. After rearranging this equation, we get Cvt dln P is equals to minus in bracket nr plus Cvt dln V. Now we know the equation for relationship between Cp and Cv is Cp minus Cv is equals to nr. Rearranging this equation, then we get Cp is equals to Cv plus nr. Putting this value in equation and cancelling T from both sides, we get Cv into dln P is equals to minus Cp dln V. After rearranging again this equation, that is moves Cv from left hand side to the denominator of right hand side, we get dln P is equals to minus Cp upon Cv dln V. Since we replace Cp by Cv is equals to gamma, then we get dln P is equals to minus gamma dln V. Integrate this equation within a suitable limits, that is for P we use limit between P1 to P2 and for V we use limit within V1 to V2. Then we get integration of dln P within a limit P1 to P2 is equals to minus gamma into integration of dln V within a limit V1 to V2. After solving this equation, we get in bracket ln P P1 to P2 is equals to minus gamma into ln V V1 to V2. Putting this equation in simple logarithmic form, we get ln P2 upon P1 is equals to minus gamma V2 upon V1. We remove the negative sign from the left side. We inverse the value of V2 by V1 to V1 by V2. Then we get ln P2 by P1 is equals to gamma into ln V1 by V2. Move the gamma in power of volume, that is V1 by V2, then we get ln P2 upon P1 is equals to ln V2 by V1 raised to gamma. We removed logarithm from both sides and gamma value is separated for both the V1 and V2. Then we get P1 by P2 is equals to V1 raised to gamma divided by V2 raised to gamma. Finally, after rearranging this equation, we get P1 V1 raised to gamma is equals to P2 V2 raised to gamma is equals to constant. This is expression for relationship between pressure and volume. In this lecture, we study most important expression showing relationship between pressure and volume. In the next lecture, we study two most important expression, that is, second is relationship between temperature and volume, and third is relationship between pressure and temperature. With this, we conclude our today's lecture here. I think all of you satisfied with this knowledge. If any query about content, comment me in comment box. If you like this video, please press the like button and don't forget to subscribe here, and also click on bell icon for the notification of my new video. Thank you very much for watching this video.